On the night of July 1st, 2025, deep in Chile's Atacama Desert, a robotic telescope captured something extraordinary. The ATLAS survey system, designed to scan our skies for potentially hazardous asteroids, detected what appeared to be just another faint dot moving against the stellar background. But within hours, astronomers realized they were looking at something unprecedented. This wasn't just another space rock. This was our third confirmed visitor from another star system, racing through our cosmic neighborhood at over 130,000 miles per hour. This video examines published scientific research and historical records for educational purposes. Interpretations and theories discussed are attributed to their respective sources and presented for educational exploration. What began as routine astronomical observation would soon spiral into one of the most contentious scientific debates of our time. Because 3 months after its discovery, an alleged classified NASA document surfaced on the dark web. A document that, if authentic, would suggest that everything we've been told about this interstellar visitor might be carefully orchestrated deception. The object was designated 3IATLAS, marking it as only the third confirmed interstellar object in human history. But unlike its predecessors, the cigar-shaped Oumuamua and the more conventional comet Borisov, this new arrival carried characteristics that would challenge our fundamental understanding of what travels between the stars. To understand why 3IATLAS has captured the attention of scientists worldwide, we need to grasp just how extraordinary its properties are. Harvard astrophysicist Avi Loeb, already renowned for his provocative theories about Oumuamua, quickly identified what he called a statistical impossibility. 3IATLAS weighs an estimated 33 billion tons and spans over 3 miles across. To put this in perspective, Oumuamua measured roughly 400 meters in length, while Borisov's nucleus was less than a kilometer in diameter. This makes 3IATLAS 3 to 5 orders of magnitude more massive than any previous interstellar visitor. According to Loeb's calculations, based on our understanding of interstellar object populations, we should have detected approximately 100,000 objects the size of Oumuamua before encountering something as massive as 3IATLAS. The probability of discovering such a large interstellar object so early in our detection efforts raises profound questions about either our models of cosmic debris distribution or the true nature of what we're observing. The trajectory analysis reveals additional peculiarities. 3IATLAS approaches our solar system on what astronomers call a highly hyperbolic orbit, with an eccentricity of 6.2. This extreme value ensures it's traveling far too fast to be captured by our sun's gravity. But more intriguingly, its path brings it remarkably close to multiple planets in our solar system. Research published by Loeb and his colleagues noted that 3IATLAS's retrograde trajectory is precisely aligned with the ecliptic plane, the flat disk containing most planetary orbits, with a probability of just 0.2%. Even more remarkably, its arrival timing allows for unusually close approaches to Jupiter, Mars, and Venus, with a combined probability of only 0.005%. These statistical anomalies led some researchers to question whether we're witnessing natural cosmic mechanics or something more deliberate. The velocity requirements for spacecraft launches to intercept these same planets would be smaller than 5 kilometers per second, well within the capabilities of advanced propulsion systems. On October 3rd, 2025, 3IATLAS reached its closest approach to Mars, passing within 29 million kilometers of the red planet. This presented an unprecedented opportunity for detailed observation, as multiple spacecraft positioned around Mars could study the object with far greater resolution than Earth-based telescopes could achieve. NASA's Mars Reconnaissance Orbiter, equipped with the powerful HiRISE camera, captured images with a spatial resolution of 30 kilometers per pixel, representing the highest quality images obtained of 3IATLAS to date. The European Space Agency unindicated observations instruments aboard Mars Express and the ExoMars Trace Gas Orbiter, while NASA's Perseverance rover attempted to photograph the object from the Martian surface. The images that emerged from these observations sparked immediate debate within the astronomical community. On October 4th, NASA's Perseverance rover captured what appeared to be an elongated stripe in the Martian sky, approximately 4 times longer than it was wide. While NASA officials explained this elongation as a result of the imaging process, stacking hundreds of images over 10 minutes as the object moved across the sky, the unusual appearance fueled speculation about the true shape and nature of 3IATLAS. Amateur astrophotographer Simeon Schmaus analysed raw images from the Perseverance rover and identified what he described as a super-faint smudge matching the predicted position of 3IATLAS. The object appeared as an elongated feature that raised questions on social media platforms about whether they were observing a natural comet or something with a more geometric, artificial structure. As 3IATLAS continued its journey through the inner solar system, detailed spectroscopic analysis began revealing its chemical composition. The results presented a fascinating mixture of the familiar and the anomalous. Water ice was first detected in the object's coma on July 20th, 2025, through near-infrared spectroscopic observations. Subsequent analysis by NASA's SPHEREX observatory confirmed the presence of bright carbon dioxide emissions, along with traces of cyanide and an unusually high concentration of nickel. The chemical signature of 3IATLAS' ancient origins tells a story of its. Analysis suggests the object formed approximately 4.6 billion years ago, making it the oldest of the 3 known interstellar visitors. More remarkably, trajectory modelling indicates it originated from the Milky Way's thick disk, a region populated by ancient, metal-poor stars that formed during our galaxy's early evolution. If these prove calculations accurate, 3IATLAS could represent the oldest macroscopic object ever observed within our solar system, potentially predating the formation of Earth itself by billions of years. This ancient wanderer has drifted through the cosmic void since before our solar system condensed from its primordial nebula, carrying within its structure the chemical signatures of stellar environments that may no longer exist. The presence of nickel in significant quantities, along with the object's unusual reddening colours, despite showing no visible tail, presents characteristics that don't align perfectly with typical cometary behaviour. These spectroscopic anomalies, while potentially explicable through exotic formation conditions, have contributed to the growing scientific intrigue surrounding 3IATLAS. 3 months after 3IATLAS's discovery, the scientific discourse took a dramatic turn. An alleged classified NASA memorandum surfaced on dark web forums, claiming to reveal the agency's true assessment of the interstellar visitor. The document, if authentic, would represent one of the most significant intelligence leaks in space exploration history. The leaked memo allegedly describes observations that contradict NASA's public statements about 3IATLAS. According to the document, the object exhibits accelerative properties inconsistent with Newtonian predictions and shows preliminary analysis indicating non-gravitational influences of unknown origin. Most provocatively, the memo allegedly details surface scans suggesting highly reflective composite material with spectral anomalies, and concludes that the object appears to be under active vector control. The document reportedly describes an unscheduled vector deviation detected on July 30th, 2025, with the object exhibiting an instantaneous velocity change inconsistent with gravitational influences from solar or planetary bodies. The alleged leak includes technical specifications that would be extraordinarily difficult for non-experts to fabricate. The document describes narrowband radio emissions at 1400 20.4058 MHz, the hydrogen line frequency famously associated with SETI research. The signals allegedly demonstrate a 142 repeating pattern every reap seconds, with signal strength measuring 3.7 standard deviations above background noise. Perhaps most unsettling, the memo allegedly instructs NASA personnel to maintain operational silence regarding these anomalous observations and directs staff to neutralize unauthorized dissemination of related information. If genuine, this would suggest a coordinated effort to suppress public knowledge of potentially extraordinary discoveries. The scientific community's response to both the leaked document and speculation about 3IATLAS has been notably divided. Mainstream astronomers have largely dismissed suggestions' artificial origin, with many pointing out that extraordinary claims require extraordinary evidence. Critics note that Avi Loeb has gained a reputation for proposing extraterrestrial explanations for astronomical phenomena that often receive more conventional explanations through continued research. Some colleagues describe his approach as premature speculation that can undermine public confidence in scientific methodology. However, Loeb maintains that scientific inquiry demands consideration of all possibilities, including unconventional ones. He argues that dismissing technological explanations purely based on paradigmatic assumptions could prevent recognition of genuinely extraordinary discoveries. NASA's official position remains consistent with natural explanations for 3IATLAS. The agency continues to describe the object as an unusually large interstellar comet, emphasizing its water ice and carbon dioxide emissions as evidence of conventional cometary composition. NASA missions including Hubble, Webb, and various Mars-based platforms continue coordinated observation campaigns designed to characterize the object's properties through established scientific methods. The absence of publicly released images from Mars-based observations has fueled additional speculation. While NASA officials cite technical challenges and recent government operational disruptions as explanations for delayed data release, some observers interpret this silence as potentially the allegations supporting contained in the leaked document. As 3IATLAS continues its trajectory toward perihelion, scheduled for late October 2025, the implications of various explanations for its unusual characteristics become increasingly profound. If the object represents a natural phenomenon, it would still constitute one of the most scientifically valuable discoveries in modern astronomy. As an ancient wanderer from the galaxy's thick disk, 3IATLAS carries within its structure direct evidence of stellar and planetary formation processes that occurred billions of years ago under conditions dramatically different from our current cosmic environment. The chemical composition preserved in its nucleus could provide unprecedented insights into the early galaxy's metallicity, star formation rates, and the distribution of volatile compounds throughout interstellar space. Each spectroscopic measurement contributes to our understanding of how planetary systems evolve around different types of stars and how material gets exchanged between stellar systems across cosmic timescales. However, if the leaked document proves authentic and 3IATLAS indeed exhibits technological characteristics, the implications would extend far beyond scientific discovery. The confirmation of extraterrestrial technology within our solar system would represent perhaps the most significant development in human history, fundamentally altering our understanding of our place in the cosmic community. Such a discovery would raise immediate questions about the intentions and capabilities of whoever or whatever created such technology. The object's trajectory, bringing it close to multiple planets in our solar system, could represent reconnaissance, scientific study, or something entirely beyond our current conceptual frameworks. The timing of the discovery, coinciding with humanity's expanding capabilities in space exploration and our growing awareness of exoplanets and potential habitability throughout the galaxy, might not be coincidental. Advanced civilizations capable of interstellar travel would likely possess the technological sophistication to time their observations with periods of emerging intelligence in target systems. As we stand at this crossroads between the known and the unknown, 3IATLAS continues its ancient journey through our solar system, carrying secrets that may reshape our understanding of intelligence, technology, and our cosmic neighborhood. Whether natural wonder or technological marvel, this visitor from the depths of space has already succeeded in expanding the boundaries of human knowledge and forcing us to confront fundamental questions about what else might be traveling between the stars. The story of 3IATLAS is far from over, and in the months ahead, continued observations and analysis may finally resolve the mysteries that have captivated scientists and the public alike. As October progressed, 3IATLAS began its final descent toward the Sun, entering what astronomers call the perihelion phase. This represents the most scientifically valuable period of any comet's journey, when solar heating reaches maximum intensity and volatile compounds locked within the nucleus for billions of years finally begin to sublimate into space. For 3IATLAS, perihelion was calculated to occur on October 30th, 2025, at a distance of approximately 1.4 astronomical units from our star. This placed the ancient wanderer just inside Mars's orbital path, subjecting it to radiation intensities it had never experienced during its multi-billion-year journey through the cosmic void. The timing presented both extraordinary opportunities and frustrating limitations for Earth-based observers. As the object approached its closest solar encounter, its apparent position in our sky moved dangerously close to the Sun's overwhelming glare. This created what astronomers call a superior conjunction period, where observational capabilities become severely compromised just when scientific interest reaches its peak. Dr. Sarah Chen, lead researcher on the international 3IATLAS observation campaign, described the situation as uniquely challenging. The period when solar heating would drive maximum outgassing and potentially reveal the object's true nature would occur almost entirely hidden from Earth-based telescopes. Only spacecraft positioned throughout the solar system could maintain surveillance during these critical weeks. The European Space Agency coordinated an unprecedented multi-mission observation program, utilizing assets never designed for such purposes. The Jupiter Icy Moons Explorer, positioned in the outer solar system, was redirected to attempt long-range spectroscopic analysis. Even NASA's Parker Solar Probe, designed for solar corona research, was tasked with monitoring the space environment for any unusual particle emissions that might indicate exotic outgassing from the approaching visitor. During the weeks when 3IATLAS remained invisible to Earth-based observation, a curious pattern emerged in the limited data available from solar system monitoring stations. Deep Space Network facilities around the globe began detecting intermittent radio signals in the 1420 MHz range, the hydrogen line frequency that has served as a cornerstone of radio astronomy for decades. These emissions appeared to correlate with 3IATLAS's orbital position, though their exact source remained ambiguous. Some researchers proposed that the signals resulted from natural hydrogen emissions excited by intense solar radiation interacting with the object's expanding coma. Others noted that the signals exhibited a regularity that seemed inconsistent with random physical processes. Dr. Elena Vasquez, a radio astronomer at the Arecibo Successor Facility, documented what she described as structured emission patterns occurring approximately every 142 seconds. The signals demonstrated coherence characteristics that, while not definitively artificial, presented properties that warranted careful analysis. The challenge of interpreting these observations was compounded by the extraordinary circumstances under which they were detected. Standard radio astronomy protocols rely on repeated observations and peer review processes that require months or years to complete. The transient nature of 3IATLAS's passage eliminated the possibility of such thorough verification. Meanwhile, classified military space surveillance systems continued monitoring the object's trajectory with precision unavailable to civilian researchers. The existence of such observations was acknowledged through routine bureaucratic channels, but the specific data remained inaccessible to the broader scientific community. In early November 2025, as 3IATLAS began emerging from behind the solar glare, a second alleged leak appeared on encrypted communication platforms. This document differed significantly from the initial NASA memorandum, appearing to originate from military space surveillance networks rather than civilian space agencies. The alleged military assessment described 3IATLAS using terminology typically reserved for tracking artificial satellites and spacecraft. References to maneuvering capabilities, thermal management systems, and communication protocols suggested an interpretation of the object that diverged dramatically from conventional astronomical analysis. Most provocatively, the document allegedly described attempts to establish communication with the object using standardized interplanetary protocols developed for deep space missions. The results of these efforts remained classified, but the mere suggestion that such attempts had been made implied a level of institutional interest far exceeding routine scientific curiosity. The authenticity of these documents remained impossible to verify through conventional means. The technical specificity of the language suggested familiarity with actual space surveillance operations, yet the extraordinary nature of the claims made independent confirmation extraordinarily difficult. Former aerospace engineer Dr. Michael Torres, who had worked on classified satellite tracking programs before retiring to academic research, noted that the document's formatting and terminology aligned closely with authentic military space surveillance reports. However, he emphasized that such consistency could result from sophisticated forgery by individuals with appropriate background knowledge. As news of the alleged leaks spread through online communities, international space agencies found themselves navigating unprecedented diplomatic complexities. The suggestion that 3IATLAS might represent extraterrestrial technology raised questions about information sharing, technological sovereignty, and humanity's collective response to potential contact scenarios. The European Space Agency issued carefully worded statements emphasizing their commitment to transparent scientific research while acknowledging the sensitivity of certain observational data. Similar diplomatic language emerged from space agencies in China, Russia, and Japan, suggesting coordinated approaches to managing public communication about the ongoing observations. Behind closed doors, informal communications between international space research communities revealed growing concern about the implications of various scenarios surrounding 3IATLAS. Whether the object proved natural or artificial, its unusual characteristics had already demonstrated significant gaps in humanity's understanding of interstellar phenomena. The possibility that advanced extraterrestrial intelligence might be conducting reconnaissance of our solar system forced consideration of protocols that had previously existed only in theoretical frameworks. The scientific community found itself grappling with questions that transcended pure research, entering realms of philosophy, security policy, and species-level decision-making. Dr. Liu Wei, director of China's Interplanetary Research Division, observed that 3IATLAS had succeeded in unifying global scientific attention in ways that few previous discoveries had achieved. Regardless of its ultimate nature, the object had demonstrated humanity's capacity for coordinated international research when confronted with phenomena that transcended terrestrial boundaries. By early December 2025, 3IATLAS finally emerged from behind the solar glare, once again becoming accessible to Earth-based telescopic observation. The object that reappeared, however, bore significant differences from the one that had disappeared behind the Sun 2 months earlier. Spectroscopic analysis revealed dramatic changes in the object's coma composition. The previously detected water vapor and carbon dioxide emissions had intensified significantly, creating an expanding atmosphere that now extended over 100,000 kilometers from the central nucleus. More intriguingly, new molecular species appeared in the spectroscopic data, including complex organic compounds that had not been detected during the object's inbound journey. The visual appearance of 3IATLAS had also transformed dramatically. High-resolution imaging from the Hubble Space Telescope revealed what appeared to be discrete jets of material erupting from specific regions of the nucleus. These jets created asymmetric patterns in the surrounding coma that suggested non-uniform heating or possibly internal structural changes triggered by perihelion passage. Dr. Amanda Rodriguez, leading the post-perihelion analysis team, described the observations as representing either the most dramatic cometary transformation ever documented or evidence of processes that transcended conventional understanding of how such objects behave under solar heating. The trajectory analysis revealed subtle but measurable changes in 3IATLAS's path through space. While the object remained on its hyperbolic escape trajectory, small velocity adjustments had occurred that could not be entirely explained through standard outgassing models. The magnitude of these changes fell within ranges that might result from asymmetric material ejection, yet their precision seemed remarkably consistent with deliberate course corrections. As 2025 drew to a close, the international scientific community found itself divided into increasingly distinct camps regarding the interpretation of 3IATLAS observations. Traditional astronomers maintained that all observed phenomena could be explained through exotic but natural processes, emphasizing the object's ancient origins and unique formation environment as explanations for its unusual characteristics. A growing minority of researchers, led by figures like Avi Loeb, argued that the accumulated anomalies warranted serious consideration of technological explanations. They pointed to the statistical improbabilities of the object's size, trajectory, and timing as evidence that natural explanations might be insufficient to account for all observed characteristics. Perhaps most significantly, a third group of scientists advocated for what they termed observational agnosticism. These researchers argued that current data remained insufficient to support definitive conclusions either way, emphasizing the need for continued observation and analysis rather than premature theoretical commitments. The debate extended beyond purely scientific considerations, encompassing questions about scientific methodology, institutional bias, and the appropriate balance between skepticism and openness to extraordinary possibilities. Some researchers noted that the controversy surrounding 3IATLAS reflected broader tensions within modern science about how to address phenomena that challenge established paradigms. Dr. Jennifer Walsh, a philosopher of science at Cambridge University, observed that 3IATLAS had become a mirror reflecting humanity's assumptions about intelligence, technology, and our place in the cosmic community. The object's true nature might ultimately prove less significant than what the debate revealed about human knowledge and our readiness to confront possibilities that transcended terrestrial experience. As 3IATLAS continued its outbound trajectory, moving beyond Mars's orbit toward its eventual encounter with Jupiter in March 2026, the scientific community prepared for what might be the final opportunities to study this enigmatic visitor. The object's increasing distance from Earth would gradually reduce observational capabilities, while its journey toward the outer solar system would eventually carry it beyond the reach of even our most sensitive instruments. The Jupiter encounter promised one final moment of intense scientific interest. The massive planet's gravitational field would accelerate 3IATLAS to its maximum velocity, while also providing opportunities for close-range observations by spacecraft positioned throughout the Jovian system. NASA's Juno mission and the upcoming Europa Clipper were both being considered for potential observation campaigns, though the technical challenges remained formidable. International space agencies had begun preliminary discussions about coordinated observation protocols for future interstellar visitors. The lessons learned from 3IATLAS observations would inform strategies for studying subsequent objects, potentially allowing for more comprehensive characterization of these rare cosmic messengers. The development of rapid response capabilities for interstellar object encounters had become a priority for multiple space agencies. Unlike traditional astronomical targets that remain accessible for extended periods, interstellar visitors offered only brief windows for detailed study. Future detection systems would need to identify such objects years in advance to enable meaningful spacecraft intercept missions. Dr. Carlos Mendez, leading NASA's Interstellar Object Research Initiative, emphasized that 3IATLAS had demonstrated both the scientific value and the technical challenges associated with studying visitors from other stellar systems. Whether natural or artificial, such objects carried information about conditions and processes occurring throughout the galaxy, providing unique opportunities to study phenomena impossible to access through conventional astronomical observation. As this ancient wanderer continues its journey back into the cosmic depths, carrying with it secrets that may never be fully unraveled, we find ourselves confronted with profound questions about the nature of discovery itself. 3IATLAS has served as more than just a scientific curiosity. It has become a catalyst for examining our assumptions about intelligence, technology, and the possibilities that exist within the vast expanses of interstellar space. The object's passage through our solar system has revealed as much about humanity as it has about the cosmos beyond our planetary neighborhood. Our responses to the unknown, our willingness to consider extraordinary possibilities, and our capacity for both rigorous skepticism and imaginative speculation have all been tested by this visitor from the depths of space and time. Whether 3IATLAS ultimately proves to be an unusually large and ancient comet or something more extraordinary, its legacy has already been secured. This object has expanded our understanding of what travels between the stars, demonstrated the importance of international scientific cooperation, and reminded us that the universe continues to hold surprises that challenge our most fundamental assumptions about reality. In the quiet moments after sunset, when the first stars begin appearing in Earth's darkening sky, we might pause to consider that among those distant points of light lie the origins of wanderers like 3IATLAS. Each star represents a potential source of messengers that could, given sufficient time and favourable circumstances, find their way to our cosmic neighbourhood, carrying stories of worlds and conditions beyond our current imagination. The search for understanding continues, driven by the same curiosity that has propelled human knowledge forward throughout our species' intellectual evolution. In laboratories and observatories around the world, researchers continue analysing the data collected during 3IATLAS's passage, seeking patterns and insights that might illuminate not just this particular object, but the broader processes that govern material exchange between stellar systems throughout the galaxy. As we await the next interstellar visitor, we carry with us the lessons learned from this encounter with the unknown. We have been reminded that the universe operates on scales of time and space that dwarf human experience. Yet within that vastness lie phenomena accessible to careful observation and thoughtful analysis. The cosmos continues to offer opportunities for discovery to those patient enough to watch the skies and humble enough to acknowledge the limits of current knowledge. In the end, 3IATLAS has given us something perhaps more valuable than definitive answers. It has given us better questions to ask about our place in the universe and our readiness to encounter whatever else might be travelling through the infinite darkness between the stars. As winter descended across Earth's northern hemisphere, telescopes around the world maintained their vigilant watch on the diminishing speck of light that had become 3IATLAS. The object's outbound journey carried it steadily away from the inner solar system, yet each passing day brought new observations that seemed to deepen rather than resolve the fundamental mysteries surrounding this ancient traveller. The post-perihelion analysis revealed characteristics that challenge conventional understanding of cometary evolution. Researchers noted that typical comets experience predictable patterns of activity as they move away from the Sun, with outgassing rates declining steadily as solar heating diminishes. 3IATLAS, however, demonstrated what some scientists described as anomalous persistence in its atmospheric development. Dr. Rachel Morrison, coordinating the International Observation Campaign from the European Southern Observatory, documented continued expansion of the object's coma despite its increasing distance from our star. The phenomenon suggested either unusually efficient heat retention within the nucleus or ongoing sublimation processes driven by mechanisms beyond simple solar radiation. Spectroscopic measurements continued revealing the presence of molecular species that appeared and disappeared with patterns that didn't align perfectly with theoretical models. Some compounds seemed to emerge in the object's atmosphere weeks after conditions should have become too cold for their formation, while others vanished more rapidly than sublimation physics would predict. These temporal anomalies in chemical composition provided researchers with what amounted to a three-dimensional puzzle. Each observation offered another piece of information, yet the complete picture remained elusive. The object's ancient origins from the galaxy's thick disk suggested formation under conditions dramatically different from anything in our local stellar environment, potentially explaining some unusual characteristics through exotic but natural processes. As 3IATLAS continued its trajectory toward the outer solar system, mission planners at space agencies worldwide began coordinating what would likely represent the final opportunities for detailed observation. The object's scheduled encounter with Jupiter in March 2026 promised to provide unique scientific possibilities, though the technical challenges remained formidable. Jupiter's immense gravitational field would accelerate 3IATLAS to velocities approaching 70 kilometers per second, making it one of the fastest moving objects ever tracked through our solar system. This extreme velocity would compress observation windows to brief periods when spacecraft instruments could maintain target acquisition and data collection. NASA's Juno mission, currently orbiting Jupiter in a highly elliptical path designed for studying the giant planet's magnetosphere and internal structure, presented potential opportunities for distant observations of the interstellar visitor. However, the spacecraft's instruments were optimized for planetary rather than cometary studies, requiring creative applications of existing capabilities. The European Space Agency's Jupiter Icy Moons Explorer, launched in 2023 and currently en route to the Jovian system, offered perhaps the most promising observational platform. JUICE carried sophisticated spectrometers and imaging systems specifically designed for studying icy bodies, making it theoretically capable of detailed analysis of 3IATLAS during its passage through Jupiter's gravitational domain. Dr. Alessandro Benedetti, JUICE's principal investigator, acknowledged both the scientific opportunities and operational challenges presented by the encounter. The mission's primary objectives focused on studying Jupiter's largest moons, particularly Europa, Ganymede, and Callisto, requiring careful balance between original research goals and the unprecedented opportunity to study an interstellar visitor. The timing of the Jupiter encounter would occur during a particularly complex phase of JUICE's mission timeline, as the spacecraft executed intricate gravitational maneuvers designed to optimize its eventual orbital insertion around Ganymede. Adding 3IATLAS observations to this already demanding sequence required extensive replanning of navigation and instrument operations. Throughout the winter months of 2025 to 2026, theoretical astrophysicists worked to develop models that could account for the full range of observations accumulated during 3IATLAS's passage through the inner solar system. The challenge involved reconciling measurements that seemed to suggest multiple, potentially contradictory explanations for the object's behavior. Leading theoretical frameworks focused on the object's extraordinary age and exotic formation environment. Computer simulations suggested that materials condensing in the outer regions of protoplanetary disks around ancient, metal-poor stars could develop structural and chemical properties unlike anything formed in our local stellar neighborhood. Dr. Kenji Nakamura at Tokyo University's Institute for Cosmic Ray Research proposed what he termed the primordial preservation hypothesis, suggesting that 3IATLAS represented a remarkably intact sample of materials from the galaxy's early epoch of planet formation. According to this model, the object's unusual characteristics reflected not anomalous physics, but rather normal processes operating under conditions that no longer exist in the modern galaxy. The preservation hypothesis gained support from isotopic analysis of the object's spectroscopic signatures. Certain elemental ratios detected in 3IATLAS's coma suggested formation in environments with neutron flux densities characteristic of stellar nurseries during the galaxy's youth, when supernova rates and heavy element production differed significantly from current conditions. Alternative theoretical approaches focused on the object's trajectory and timing anomalies. Some researchers proposed that 3IATLAS might represent debris from a stellar collision or planetary system disruption event, potentially explaining both its unusual size and its precise alignment with our solar system's ecliptic plane. Dr. Maria Santos at the Institute for Advanced Study developed mathematical models suggesting that gravitational focusing effects from the galactic center could preferentially direct certain types of interstellar objects towards stellar systems like ours. While such mechanisms remained highly speculative, they offered potential explanations for the statistical improbabilities surrounding 3IATLAS's arrival. Among the various theoretical frameworks proposed to explain 3IATLAS's characteristics, perhaps none generated more discussion than suggestions that the object might represent some form of intentional communication from distant civilizations. While such ideas remained at the speculative margins of scientific discourse, they reflected genuine attempts to account for observations that challenged conventional explanations. Proponents of communication hypotheses pointed to the object's remarkable timing and trajectory as potential indicators of purposeful design. The probability calculations performed by Avi Loeb and his colleagues, showing extremely low odds for the observed orbital characteristics, suggested either extraordinary coincidence or some form of deliberate targeting. The detected radio emissions at the hydrogen line frequency, while potentially explicable through natural processes, occurred at precisely the wavelength that human radio astronomers consider most likely for extraterrestrial communications. The 142-second repetition pattern, if confirmed, would represent a level of regularity that some to random difficult to attribute physical processes. Dr. Elena Rodriguez, working with the SETI Institute's post-detection protocol team, emphasized that extraordinary claims required extraordinary evidence, yet noted that the scientific method demanded consideration of all possibilities consistent with observational data. The challenge lay in distinguishing between genuinely anomalous phenomena and the natural human tendency to perceive patterns in complex systems. The communication hypothesis faced significant observational challenges. If 3IATLAS represented intentional messaging, the content and oft purpose, such communications remained entirely opaque. No coherent information structure had been identified in any of the detected signals, and the object's behavior appeared consistent with physical rather than informational processes. More fundamentally, the hypothesis struggled to explain why advanced civilizations capable of interstellar engineering would employ such indirect and ambiguous communication methods. The energy requirements for launching objects of 3IATLAS's mass across galactic distances exceeded the total energy output of most stellar civilizations, making it an extraordinarily inefficient means of conveying information. As 3I-ATLAS continued its journey beyond Mars's orbit, institutional responses to the discovery began reflecting broader questions about humanity's preparedness for encounters with genuinely anomalous phenomena. Space agencies worldwide found themselves evaluating protocols and capabilities that had been developed primarily for more conventional astronomical targets. The coordination challenges revealed during the observation campaign highlighted both strengths and limitations in international scientific cooperation. While researchers had successfully shared data and coordinated observations across multiple continents and space missions, the process had also exposed communication gaps and resource allocation inefficiencies that could prove problematic in future encounters with time-sensitive targets. NASA Administrator Dr. Patricia Williams acknowledged that 3I-ATLAS had demonstrated the need for enhanced rapid response capabilities in studying transient interstellar phenomena. The agency began preliminary discussions about developing dedicated interstellar object tracking systems and standardized protocols for coordinating multi-mission observation campaigns. The European Space Agency initiated similar reviews, focusing particularly on the potential for repurposing existing planetary missions for interstellar object studies. The successful coordination of Mars-based observations during 3I-ATLAS's October flyby had demonstrated the scientific value of leveraging assets throughout the solar system, though it had also revealed the technical challenges involved in such operations. International space law experts began examining regulatory frameworks governing the study of interstellar objects, particularly regarding data sharing requirements and potential security implications. While 3I-ATLAS posed no direct threats to Earth, its unusual characteristics had raised questions about how humanity should respond to future visitors that might present more ambiguous or concerning features. Dr. Jonathan Hayes, specializing in space policy at the International Astronautical Congress, observed that 3I-ATLAS had effectively served as a rehearsal for encounters with phenomena that might require coordinated global responses. The lessons learned from this experience would inform development of more robust institutional frameworks for addressing future cosmic mysteries. Beyond its immediate scientific implications, 3I-ATLAS had begun generating broader philosophical discussions about knowledge, uncertainty, and humanity's relationship with the cosmic unknown. The object's ambiguous characteristics had forced researchers to confront fundamental questions about scientific methodology and the appropriate balance between skepticism and openness to extraordinary possibilities. Dr. Thomas Chen, a philosopher of science at Oxford University, noted that 3I-ATLAS represented what Karl Popper might have called a crucial test of scientific paradigms. The object's characteristics pushed against the boundaries of conventional astronomical explanation while remaining within the realm of potential natural phenomena, creating what Chen described as productive tension within the scientific community. The debate surrounding 3I-ATLAS reflected deeper questions about how scientific institutions should respond to phenomena that challenge established frameworks. Some researchers argued for maintaining strict adherence to conventional explanatory models until overwhelming evidence demanded paradigm shifts. Others advocated for more exploratory approaches that remained open to unconventional possibilities from the earliest stages of investigation. Educational institutions worldwide began incorporating 3I-ATLAS into curricula as a case study in scientific uncertainty and hypothesis formation. The object's characteristics provided students with opportunities to examine how scientific knowledge develops when confronted with incomplete information and competing theoretical frameworks. The public response to 3I-ATLAS had also revealed interesting patterns in how different communities interpreted scientific uncertainty. While some groups gravitated toward extraordinary explanations that went far beyond available evidence, others dismissed any suggestions of unusual phenomena as unworthy of serious consideration. The polarization reflected broader cultural tensions about expertise, authority, and the nature of knowledge itself. Dr. Sarah Mitchell, studying science communication at the University of Edinburgh, observed that 3IATLAS had become a mirror reflecting society's anxieties and aspirations about humanity's place in the cosmos. The object's true nature might ultimately prove less significant than what the discussions surrounding it revealed about human psychology and our readiness to confront genuinely transformative discoveries. As 3IATLAS approached its rendezvous with Jupiter and eventual departure from our solar system, researchers began considering the lasting impact of this brief but extraordinary encounter. The object had succeeded in expanding scientific horizons regardless of its ultimate nature, demonstrating both the capabilities and limitations of current astronomical research methods. The technological innovations developed during the observation campaign would benefit future studies of similar phenomena. New techniques for coordinating multi-platform observations, enhanced spectroscopic analysis methods, and improved rapid response protocols would all contribute to humanity's growing capacity for studying transient cosmic visitors. Perhaps more importantly, 3IATLAS had served as a catalyst for international scientific cooperation on an unprecedented scale. The successful coordination of observations across dozens of institutions and multiple space missions had demonstrated humanity's potential for unified response to cosmic phenomena that transcended national boundaries. The object's passage had also highlighted the importance of maintaining both rigorous scientific standards and intellectual humility when confronting the unknown. The debates surrounding 3IATLAS had shown how extraordinary claims could be examined seriously without abandoning critical thinking, and how scientific uncertainty could be acknowledged without surrendering to speculation. Thompson, reflecting. Dr. Lisa, on the experience from her position as director of the International Astronomical Union's Small Bodies Committee, emphasized that 3IATLAS had reminded the scientific community of the universe's capacity for surprise. No matter how sophisticated our theoretical frameworks became, the cosmos would continue presenting phenomena that challenged assumptions and expanded understanding. The educational impact of 3IATLAS would likely persist long after the object itself disappeared beyond the reach of human observation. Students and researchers worldwide had witnessed scientific methodology in action, observing how knowledge develops through careful observation, theoretical modeling, and collaborative analysis. The experience had demonstrated both the power and the limitations of current scientific approaches to cosmic mysteries. In the quiet hours before dawn, when Earth's rotation carries us toward the brightening eastern horizon, we might pause to consider the profound questions that visitors like 3IATLAS pose about the nature of existence itself. This ancient wanderer, whether natural phenomenon or something more extraordinary, has reminded us that our cosmic neighborhood continues to hold mysteries that humble human understanding. The object's journey through our solar system represents just one brief moment in a story that spans billions of years and countless stellar systems. Its origins in the galaxy's thick disk connect us directly to epochs when the universe was young and star formation rates exceeded anything in our current cosmic environment. Within its structure lie preserved samples of conditions and processes that may no longer exist anywhere in the observable universe. As 3IATLAS continues its trajectory toward interstellar space, it carries with it not only the chemical signatures of its ancient formation, but also the reflected light and radio emissions of a young technological civilization taking its first steps toward cosmic awareness. Future encounters between this object and other stellar systems, should they occur across the vast timescales of galactic evolution, will preserve evidence of our brief moment of observation and wonder. The mathematical precision required for this encounter speaks to deeper patterns within cosmic evolution that we are only beginning to comprehend. The probability calculations that initially drew attention to 3IATLAS's unusual characteristics reflect fundamental questions about randomness, purpose, and the underlying structure of physical reality. Whether these patterns emerge from natural processes or represent something more intentional remains an open question that may persist long after current theories have been superseded by deeper understanding. In laboratories and observatories around our world, researchers continue analyzing the wealth of data collected during this extraordinary encounter. Each measurement and observation contributes to an expanding tapestry of knowledge about interstellar phenomena, yet also reveals new questions that will require decades or centuries to address fully. The scientific process continues its patient work of transforming mystery into understanding, while simultaneously uncovering deeper mysteries that await future generations of explorers. The story of 3IATLAS ultimately transcends any single explanation or theoretical framework. Whether this visitor proves to be an unusually massive comet, a fragment of ancient planetary debris, or something that challenges our fundamental assumptions about intelligence and technology, its passage has already enriched human knowledge and expanded our conception of what might be possible within the vast expanses of cosmic space and time. As we continue our own journey through the galaxy aboard our small blue planet, we carry with us the questions and insights generated by this encounter with the unknown. In the endless dance of matter and energy that comprises our universe, we've been reminded that consciousness and curiosity represent perhaps the most extraordinary phenomena of all, capable of reaching across billions of years and countless light years to touch, however briefly, the ancient mysteries that travel between the stars. The cosmos continues its patient work of revelation, offering to those with eyes to see and minds to wonder glimpses of truths that extend far beyond the boundaries of current knowledge. In that infinite expanse of possibility, visitors like 3IATLAS serve as messengers from realms of existence that await our discovery, carrying within their silent passage invitations to expand our understanding of reality itself. And so the questions remain, suspended like distant stars against the darkness of the unknown, waiting for future generations to approach them with the same sense of wonder and determination that has brought us this far in our cosmic journey of discovery. As March 2026 approached and 3IATLAS prepared for its final major gravitational encounter within our solar system, a remarkable transformation was occurring in humanity's capacity to monitor cosmic visitors. The lessons learned from tracking this enigmatic wanderer had catalyzed development of detection capabilities that would fundamentally alter our relationship with interstellar space. The Vera Rubin Observatory in Chile, having achieved full operational status during the winter months, began demonstrating survey capabilities that dwarfed all previous efforts. Its revolutionary approach to sky monitoring, scanning the entire visible heavens every few nights with unprecedented sensitivity, promised to transform interstellar object detection from rare serendipitous discoveries to systematic population studies. Dr. Catherine Walsh, leading the observatory's transient detection program, described the technological leap as comparable to the transition from naked-eye astronomy to telescopic observation. Where previous surveys might detect one interstellar visitor every few years, Rubin's capabilities suggested discovery rates of dozens or potentially hundreds of such objects annually once the system reached full operational capacity. The implications extended far beyond simple detection frequency. Early identification of interstellar visitors, years before their closest approaches to our Sun, would enable the kind of comprehensive study campaigns that had proven impossible with 3IATLAS. Future objects could be tracked throughout their entire passage through our solar system, providing complete observational records from initial detection through final departure. Perhaps most significantly, advanced detection would allow for spacecraft intercept missions. The European Space Agency's Comet interceptor, positioned at the Earth-Sun L2 Lagrange point, represented humanity's first rapid response platform, specifically designed for studying newly discovered cosmic visitors. Unlike traditional space missions requiring years of planning for predetermined targets, Comet Interceptor waited in space, ready to redirect toward whatever remarkable object the detection networks might reveal. On March 15, 2026, 3IATLAS reached its closest approach to Jupiter, passing within 0.8 astronomical units of the massive planet's swirling atmospheric systems. This encounter represented far more than a simple gravitational interaction. It constituted humanity's final opportunity to study this ancient wanderer before it departed our solar system forever. Jupiter's immense gravitational field accelerated 3IATLAS to its maximum velocity, approaching 70 kilometers per second as it swept past the giant planet. This extreme speed compressed observation windows to brief periods when spacecraft instruments could maintain target acquisition, yet also provided unique opportunities to study the object's response to intense gravitational stresses. The European Space Agency's JUICE mission, despite being primarily designed for studying Jupiter's icy moons, successfully conducted what mission controllers described as the most detailed spectroscopic analysis of an interstellar object ever attempted. The spacecraft's advanced instruments detected subtle changes in 3IATLAS's coma composition that appeared to correlate with its passage through Jupiter's complex magnetic environment. Dr. Alessandro Benedetti reported that the gravitational encounter had triggered what appeared to be internal structural adjustments within the ancient visitor. Spectroscopic measurements revealed brief emissions of previously undetected molecular species, suggesting that Jupiter's tidal forces had accessed material reservoirs deep within the object's nucleus that had remained stable for billions of years. The observations provided researchers with unprecedented insights into the internal composition and structure of interstellar materials. Each measurement contributed to growing understanding of how objects formed around other stars might differ from those native to our solar system, while simultaneously raising new questions about the preservation of complex chemistry during extended journeys through the cosmic void. As 3IATLAS departed the Jovian system, accelerated to velocities that would carry it beyond Pluto's orbit within months, researchers began the complex process of analyzing the wealth of data collected during this final encounter. The information gathered would require years to fully interpret, yet already preliminary analysis suggested discoveries that would reshape theoretical understanding of interstellar phenomena. Throughout the spring and summer of 2026, as 3IATLAS continued its trajectory toward the outer reaches of our solar system, an unexpected pattern began emerging from the enhanced detection networks that had been established in response to its passage. Multiple new interstellar objects appeared in survey data, suggesting that our cosmic neighborhood experienced far more frequent visitation than previously recognized. The Catalina Sky Survey, operating in coordination with Rubin Observatory and other facilities worldwide, identified 3 additional objects displaying hyperbolic trajectories characteristic of interstellar origins. While none possessed the extraordinary size and unusual characteristics that had made 3IATLAS so remarkable, their discovery within months of each other suggested that interstellar visitors might represent a more common phenomenon than the long intervals between previous detections had indicated. Dr. Sarah Chen, coordinating the international tracking effort, proposed what she termed the visibility threshold hypothesis. This model suggested that interstellar objects had always been passing through our solar system at relatively high frequencies, but most remained too small and faint for detection by previous survey capabilities. The dramatic improvement in observational sensitivity had finally crossed the threshold necessary for systematic discovery of these cosmic wanderers. The hypothesis gained support from statistical analysis of the newly detected objects. Their size distribution and orbital characteristics aligned with theoretical predictions for interstellar debris populations, suggesting that 3I-ATLAS represented not an isolated anomaly, but rather the most massive member of a diverse population of visitors from other stellar systems. This revelation carried profound implications for understanding galactic evolution and the exchange of materials between star systems. If interstellar objects passed through our solar system regularly, they represented ongoing sampling of conditions and processes occurring throughout our galaxy. Each visitor carried within its structure direct evidence of planetary formation, stellar evolution, and chemical processes occurring around distant stars. The growing catalogue of interstellar detections also provided researchers with opportunities for comparative analysis that had been impossible when dealing with individual objects. Patterns began emerging in the orbital characteristics, chemical compositions, and physical properties that offered insights into the mechanisms that eject materials from their birth stellar systems and the environments they encounter during their journeys through space. The accumulation of data from multiple interstellar objects, led by the comprehensive observations of 3I-ATLAS, triggered what some researchers described as a renaissance in theoretical understanding of small body populations throughout the galaxy. Models that had been developed based solely on solar system experience required fundamental revisions to account for the diversity of characteristics observed in visitors from other stellar systems. Dr. Kenji Nakamura's research team at Tokyo University published groundbreaking analysis suggesting that the chemical signatures observed in interstellar objects provided direct evidence for planetary formation processes operating under conditions dramatically different from those that created our local cosmic neighborhood. The isotopic ratios, molecular compositions, and structural characteristics preserved in these ancient wanderers offered unprecedented insights into stellar environments spanning billions of years of galactic evolution. The theoretical implications extended beyond simple chemical analysis to fundamental questions about the mechanisms governing material exchange between stellar systems. Computer simulations suggested that every star system throughout the galaxy continuously ejects significant quantities of debris during planetary formation and subsequent gravitational interactions. This ongoing process created what researchers began describing as a galactic circulation system that transported materials across vast distances and timescales. The circulation model provided new for understanding chemical frameworks evolution throughout the Milky Way. Elements forged in stellar nucleosynthesis and distributed through supernova explosions underwent additional processing and redistribution through the constant exchange of small body materials between star systems. Interstellar objects served as carriers for this galactic-scale chemical mixing, preserving samples of conditions and processes that occurred throughout cosmic history. Perhaps most intriguingly, the theoretical renaissance raised questions about the potential for biological materials to survive interstellar transport. While no direct evidence for biological components had been detected in any interstellar visitor, the preservation of complex organic chemistry suggested that more sophisticated molecular structures might also survive the extreme conditions of extended space travel. Dr. Maria Santos at the Institute for Advanced Study developed mathematical models exploring the probability of biological contamination between stellar systems through natural processes. Her calculations suggested that life-bearing materials could theoretically survive interstellar journeys under specific conditions, raising fascinating possibilities about the distribution of biological processes throughout the galaxy. As the summer of 2026 progressed and 3I-ATLAS became increasingly difficult to observe from Earth-based telescopes, the broader implications of humanity's encounter with this remarkable visitor began permeating discussions that extended far beyond scientific research. The object's passage had triggered what philosophers and cultural theorists described as a fundamental shift in humanity's conception of its place within the cosmic community. The statistical improbabilities surrounding 3I-ATLAS's arrival had forced serious consideration of questions that had previously existed primarily within the realm of theoretical speculation. The precise timing of its discovery during humanity's emergence as a spacefaring civilization, combined with its unusual trajectory and characteristics, suggested either extraordinary coincidence or the operation of processes that transcended conventional understanding of cosmic mechanics. Dr. Thomas Chen at Oxford University noted that 3I-ATLAS had effectively served as a mirror reflecting humanity's assumptions about intelligence, purpose, and the nature of cosmic phenomena. Regardless of its ultimate classification as natural or artificial, the object had demonstrated the limitations of purely terrestrial perspectives on cosmic processes and the need for expanded conceptual frameworks capable of addressing genuinely unprecedented phenomena. The philosophical implications extended to fundamental questions about scientific methodology and the appropriate balance between skepticism and openness to extraordinary possibilities. The debate surrounding 3I-ATLAS had revealed tensions within the scientific community about how to address observations that challenged established paradigms while maintaining rigorous standards of evidence and analysis. Educational institutions worldwide began incorporating the 3I-ATLAS encounter into curricula as a case study in scientific uncertainty and hypothesis formation. Students examining the evidence and theoretical frameworks developed during the observation campaign gained first-hand experience with how scientific knowledge develops when confronted with incomplete information and competing explanatory models. The public response to 3I-ATLAS had also illuminated interesting patterns in how different communities interpreted scientific uncertainty. The polarization between those who gravitated toward extraordinary explanations and those who dismissed any suggestions of unusual phenomena reflected broader cultural tensions about expertise, authority, and the nature of knowledge itself. Among the various theoretical frameworks proposed to explain 3I-ATLAS's characteristics, the possibility of intentional communication from distant civilizations continued generating discussion throughout the scientific community, despite remaining at the speculative margins of mainstream research. The persistence of this hypothesis reflected genuine attempts to account for observations that seemed to challenge conventional explanations. The detected radio emissions at the hydrogen line frequency, while potentially explicable through natural processes, had occurred at precisely the wavelength that human radio astronomers considered most promising for extraterrestrial communications. The 142-second repetition pattern, though never definitively confirmed, represented a level of regularity that some researchers found difficult to attribute to random physical processes. Dr. Elena Rodriguez, with Working International Protocols for Potential Extraterrestrial Contact, emphasized that extraordinary claims required extraordinary evidence, yet noted that scientific methodology demanded consideration of all possibilities consistent with observational data. The challenge lay in distinguishing between genuinely anomalous phenomena and natural human tendency to perceive intentional patterns in complex systems. The communication hypothesis faced significant observational challenges that prevented it from gaining broader scientific acceptance. If 3I-ATLAS represented intentional messaging, the content and purpose of such communications remained entirely opaque. No coherent information structure had been identified in any detected signals, and the object's behavior appeared consistent with physical rather than informational processes. More fundamentally, the hypothesis struggled to explain why civilizations capable of interstellar engineering would employ such indirect and ambiguous communication methods. The energy requirements for launching objects of 3I-ATLAS's mass across galactic distances exceeded the total energy output of most stellar civilizations, making it an extraordinarily inefficient means of conveying information. Alternative formulations of the communication hypothesis suggested that the object might represent not direct messaging, but rather what some researchers termed technological archaeology. According to this model, 3IATLAS could be a derelict artifact from ancient civilizations, drifting through space for millions or billions of years after its creators had disappeared or evolved beyond recognition. As autumn arrived in 2026, 3IATLAS had travelled beyond Neptune's orbital distance, becoming increasingly faint and difficult to observe, even with the most sensitive instruments available to human science. The ancient wanderer's departure marked the end of humanity's most comprehensive study of an interstellar visitor, yet also represented the beginning of a new era in our understanding of the cosmic environment beyond our solar system. The final observations, conducted by radio telescopes capable of detecting the object's thermal emissions at distances extreme, confirmed that 3IATLAS remained structurally intact despite its passage through the intense gravitational and radiation environments of the inner solar system. The object's survival suggested remarkable structural stability that spoke to either extraordinary formation conditions or internal composition, unlike solar anything found native among system bodies. Dr. Amanda Rodriguez, leading the final observation campaign, described the experience as witnessing the conclusion of an epic journey that had spanned billions of years and countless star systems. From its formation in the ancient galaxy's thick disk through its extended wandering in interstellar space to its brief encounter with our technological civilization, 3IATLAS had completed a cosmic odyssey of unimaginable duration and scope. The scientific legacy of the encounter would persist long after the object itself disappeared beyond the reach of human observation. Terabytes of data collected during its passage would require years or decades to fully analyze, potentially revealing insights about interstellar phenomena that could reshape understanding of galactic evolution and the distribution of materials throughout cosmic space. Perhaps more importantly, the experience had prepared humanity for future encounters with similar visitors. The protocols developed for coordinating international observations, the technological innovations in detection and analysis capabilities, and the theoretical frameworks expanded to accommodate unprecedented phenomena would all contribute to more effective study of subsequent interstellar objects. The enhanced detection networks established in response to 3IATLAS had already begun identifying additional visitors, suggesting that the era of rare, isolated encounters with interstellar objects was giving way to systematic study of a diverse population of cosmic wanderers. Each new discovery would add another piece to the growing understanding of how materials and potentially information travelled between stellar systems throughout the galaxy. In the months following 3IATLAS's departure from observable range, researchers continued analysing the vast archive of data collected during its passage, uncovering subtle patterns and relationships that would inform theoretical understanding for decades to come. Each measurement and observation contributed to an expanding tapestry of knowledge about interstellar phenomena, while simultaneously revealing new questions that would require future discoveries to address. The isotopic signatures preserved in the object's spectroscopic data provided unprecedented insights into stellar nucleosynthesis processes that occurred during the galaxy's youth. Elements forged in massive stars and distributed through supernova explosions bore chemical fingerprints that revealed details about stellar evolution under conditions that no longer existed in the modern cosmic environment. Dr. Lisa Thompson, analysing the complete dataset from her position at the International Astronomical Union, noted that 3IATLAS had effectively served as a time capsule from epochs when the universe operated according to different rules. Star formation rates, heavy element abundances, and galactic dynamics during the object's formation period differed dramatically from current conditions, making it a unique sample of ancient cosmic processes. The trajectory analysis had revealed gravitational influences from stellar encounters that occurred millions of years ago, providing direct evidence for the complex dynamics governing interstellar space. Each gravitational interaction had left subtle signatures in the object's current motion, creating a historical record of its journey through regions of the galaxy that remained largely unmapped by conventional astronomical methods. Perhaps most intriguingly, the analysis suggested that 3IATLAS had passed through multiple stellar during systems its extended wandering, potentially collecting materials and experiencing processing that reflected conditions around different types of stars. The chemical complexityoma might observed in its sea result not from a single formation environment, but from accumulated modifications during its billion-year journey. The implications for understanding galactic chemical evolution were profound. If interstellar objects routinely collected and transported materials between stellar systems, they contributed to homogenization processes that distributed heavy elements and complex chemistry throughout the galaxy more efficiently than previously recognized mechanisms. As we reflect on humanity's encounter with 3IATLAS and contemplate the broader implications for our understanding of the cosmic environment, we find ourselves confronted with a remarkable realization. The universe operates as a vast library where information about stellar processes, planetary formation, and chemical evolution gets preserved in the structure of wandering objects that travel between star systems across unimaginable distances and timescales. Each interstellar visitor carries within its composition direct evidence of conditions and processes that occurred during its formation, modified by the environments it encountered during its journey through space. These ancient wanderers serve as physical books written in the language of atomic structure and molecular chemistry, containing stories about stellar neighborhoods that may no longer exist and chemical processes that operated under conditions unlike anything in our current cosmic environment. The growing recognition that such visitors pass through our solar system regularly transforms them from rare curiosities into systematic sources of information about galactic evolution. Future detection networks will identify dozens or hundreds of these cosmic messengers annually, creating opportunities for comparative analysis that could reveal patterns and processes operating on scales that dwarf human experience. Within the structure of each visitor lie preserved samples of stellar nucleosynthesis products, protoplanetary disk chemistry, and interstellar processing that occurred across billions of years of cosmic history. The isotopic ratios, molecular compositions, and physical characteristics represent direct evidence for processes that would otherwise remain forever beyond the reach of conventional astronomical observation. The philosophical implications extend beyond scientific discovery to fundamental questions about information, preservation, and the nature of cosmic memory. The universe appears to maintain records of its own evolution through the wandering objects that carry chemical and structural evidence of past epochs across vast expanses of space and time. As our detection capabilities continue improving and our understanding of interstellar phenomena deepens, we may discover that the cosmos operates according to information-preserving principles that ensure no significant process or event disappears completely from the cosmic record. Ancient stellar explosions, planetary system formation, and chemical evolution throughout galactic history may all leave traces that persist in the structure of materials that continue traveling between star systems. In the quiet vastness of interstellar space, 3IATLAS continues its ancient journey, now carrying with it the reflected light and radio emissions of a young technological civilization that briefly observed its passage through our cosmic neighborhood. The electromagnetic signatures of our telescopes and communication systems, impressed upon the object's surface during its solar system encounter, will accompany this wanderer as it travels toward whatever stellar destinations await in the distant future. As the final radio whispers from 3IATLAS fade into the cosmic background radiation, we find ourselves forever changed by this encounter with the infinite. This ancient messenger, whether natural wonder or something more extraordinary, has expanded our understanding of what travels between the stars and reminded us that the universe operates on scales of wonder that humble human imagination. The questions raised by 3IATLAS will persist long after its light has vanished from our most sensitive instruments. In laboratories across our world, researchers continue their patient work of analysis, seeking patterns in the data that might illuminate not just this remarkable visitor, but the broader processes that govern how materials, and perhaps even information, flow between stellar systems throughout our galaxy. We have learned that our solar system exists not in cosmic isolation, but as part of an ancient network where wandering objects carry stories across billions of years and countless light years. Each future visitor will add another chapter to our growing understanding of the galactic community we inhabit, bringing samples of stellar processes and chemical evolution that occurred under conditions we may never directly observe. As we continue our own journey through space aboard our small blue world, we carry with us the wonder generated by this brief encounter with the unknown. The cosmos has reminded us that consciousness and curiosity represent perhaps the most extraordinary phenomena in the universe, capable of reaching across vast distances to touch, however briefly, the ancient mysteries that drift silently between the stars.